All right, and today Ryan Hickox from Dartmouth will be talking about the Roman Space Telescope High Latitude Wide Area Survey. So Ryan, thanks again, and take it away, please.
Great. Thanks, everybody. Hi, I'm Ryan Hickox. I'm one of the co-chairs of the High Latitude Wide Area Survey Definition Committee. The other co-chair, Rita Wessler, is here. I'm going to lead this presentation, but I'm sure she's available to answer questions, as are some other members of the committee as well. So first off, thank you to everyone for joining us as we give you an update on this community process. Just an outline of the talk. For the first part, I'll sort of introduce what the community process is and a little bit about the High Latitude Wide Area Survey itself. Looking at the list, this is a fairly expert audience, so I think hopefully this will go fairly quickly in 10 minutes or so, 10, 15 minutes. And then the second half of the talk, I'll discuss where we are in terms of our nominal survey plan, and what are some of the outstanding trade spaces and considerations, as well as technical questions that we need addressed. And finally, we'll discuss opportunities for everyone to continue to contribute or provide input, and some of those already are the links that are put in the chat right now. So first off, just an introduction to the core community surveys. And by the way, I have my screen here in two places, so it's on a different screen from my camera. So sorry if I'm not looking straight at it all the time. As I think most of you probably know, Roman is designed as a survey telescope, and is designed. The surveys to be carried out by Roman are designed primarily to meet some pretty ambitious science goals as laid out by the Astro 2010 decadal survey. And in order to meet those science goals, we basically have defined three core community surveys that are community led and community designed, that will take up to 75% of the observing time for the mission. And so those three surveys are a galactic bulge time domain survey that's primarily designed to identify exoplanets via microlensing. A high latitude time domain survey, whose primary aim is to look at high redshift supernovae to determine the expansion of the universe and therefore put constraints on dark energy, and other cosmological parameters. Excuse me. And then the one we'll talk about today is the High Latitude Wide Area Survey, which is a wide area of thousands of square degrees, and we'll go through what some of those parameters might actually look like. Survey including multiband imaging and slitless spectroscopy, the primary aim of which is, at least the level 1 science requirement for this, is to do cosmology via galaxy weak lensing and large-scale structure. So the top level goals for defining these surveys are to maximize the overall science return of Roman's wide field infrared surveys while meeting mission requirements focused on, as I mentioned, cosmology and exoplanets. But Roman really is an enormous step forward, as I think probably everyone on this call knows, in terms of capability of doing high resolution sensitive space-based infrared observations to an extent where its survey speed is 1,000 times faster than the Hubble Space Telescope. And so in addition to meeting these requirements as laid out by Astro 2020, our aim is to then meet those and then maximize the overall science return. And the surveys as implemented will be defined by the community based on this definition committee process that we're updating you on about today. And just to say, sorry, I forgot to mention here, the three core community surveys are these three. We also have a early definition survey that will be done, is characterized more as a general astrophysics survey, but one that is being defined early also by a community process, and that is a survey of the galactic plane. And so that's another exciting piece of this whole science puzzle. Okay, and so how everything works, we have a definition committee for each of the three core community surveys, plus one for the galactic plane early definition, and they will provide recommendations to the Roman Observations Time Allocation Committee, the ROTAC, which will then evaluate the different pieces of input from these different surveys and ultimately make a recommendation as to how Roman observing time is allocated over the first several years. And so there are lots of details in terms of how this works here, and I'll go through those as we go along. In terms of the time frame, we had an initial request for community input last year. We had a formation of the definition committees happened sort of near the end of last year, and then this year we've been primarily, this is sort of where we're at now, is that committees have been doing their work. And we had a lot of submissions from white papers, science pitches, and other input from the community that we're considering in detail. And finally, our report detailing the observations is due at the end of, or at sometime in November this year. So we're sort of really putting things together now and are in the process of starting to solidify things. And I'll give you an update on that. Okay, so in terms of the high latitude wide area survey itself, the broad architecture of this is that it consists of a large area, both imaging and spectroscopy survey. And the main driver for at least the main science driver as laid out by the science requirements for the imaging survey is weak lensing for cosmology. And so to do that, you need high angular resolution and a good PSF, depth and area, photometric coverage in the near infrared, and also some deeper, so this over a wide area to get a large number of galaxy shapes, but also deep fields to understand sensitivity limits and systematics, and also some spectroscopic data, either from space or the ground, in order to calibrate photosy. So this is, Roman, you can already see that Roman is very well designed to meet these requirements. We also have a spectroscopic component of the survey, which is designed to do cosmology using measurements of baryon acoustic oscillations and redshift space distortions. And so this will be a galaxy redshift survey from space that will also be informed by the imaging, as we'll talk about in a little bit. And there's some things required to make this happen. For example, multiple roll angles for spectroscopy to do spectral decontamination. And basically figuring out how much time you need to do this is driven to a large extent by how sensitive you can get over a given area and exposure time. So together, these are the sort of the main things for the level 1 cosmology requirements, but also a major objective for Roman is just to do a wide field infrared survey with imaging and spectroscopy to deep depths greater than 26 or so magnitude. And so this survey does that sort of in a more general sense, not just meeting these cosmology requirements. Now, one thing to emphasize, and this will become important as we go along, is that the observing time allocation is finite for any one of these surveys. In this particular case, the guidance we've been given is an allocation of 520 days total observations. And as part of our report, we'll also provide a configuration that we would recommend for an overguide of 540 days and also an underguide of 480 days. And then with that input, the ROTAC will decide what the balance between the different surveys is. And so that's what we're working from here. And it's important to remember that we had a lot of input on really amazing science programs that, as I'll mention later, we couldn't necessarily get to in this large but still limited allocation of observing time. Okay, so who are the people who are doing this? This is our wonderful group of members of the Survey Definition Committee. So the co-chairs are myself and Risa, who I think is still here on the call, plus all these other wonderful people who, a number of whom are on the call as well here today. And just to point out, and actually this is not, I realize this is missing some of our colleagues who, for example, some of our solar system colleagues. I know Rosemary Pike I think I saw her on the call today. She's another member of this committee as well. And so anyway, these are wonderful people. This is probably the most distinguished and knowledgeable group of people I've ever had the pleasure of working with. So it's been fun working with these folks. And based on a lot of input from everyone, we'll get to the point that we'll discuss today. So what is the overall timescale of this committee? Well, we had our first kickoff meeting about 6 months ago. And then at that point, we organized a process for reviewing all of the input that we got, the white papers and the science pitches. We then did a lot of reviewing and ranking and discussion of the science ideas to get a sense of what the overall landscape is. And over the summer, we've been exploring trade spaces and looking at outstanding technical questions. And so in the end of the summer here, we've then been reporting to the community for feedback and iteration. And so we've had two main opportunities to report to the committee. One was in July at the Roman Science Conference. So some of you may have seen the talk there. And then this is the second of the two virtual town halls. So thank you for joining us for this. Basically, over the next couple months, our aim is to refine trades with technical input and develop the implementation plans. And then our report is due in November. Okay, so before we get into where we currently stand, it's best to start with, I think, a discussion of what the reference design was for the high latitude wide area survey. So as part of putting the mission together, it was necessary to show that the Roman telescope specifications were sufficient to actually reach the science goals. And so in order to do that, there was a design reference mission that was developed that basically showed that Roman could actually do the science that was required. And so in a way, I think for all the surveys, this is kind of the starting point that we began with, but there have been some changes to the capabilities of the telescope, and also we get a lot of interesting science input that means we will be deviating from this. But at least to begin with, I want to give a sense of what that reference mission looks like. So the design reference mission had was primarily a wide area survey of around 2,000 square degrees, and the aim is to measure 100 million galaxy shapes at very high precision with space-based imaging, which is kind of amazing, and also get about 10 million galaxy spectroscopic redshifts. In terms of imaging, the idea was to do 2 passes to be able to get multiple rolls, fully sample the PSF, etc. In 4 bands: the Y band, J band, H band, and H and K band. So going from around 1 to 2 microns and getting out to 26 to 27th magnitude. There'd also be 4 dithers on each pass, again to improve the sampling and so that we can understand the PSF really well, which is critical for the shape measurements, and that is the overall exposures were around 140 seconds, which is basically maximizes the number of galaxies that you can detect well enough to do the shape measurements, and we'll talk a little bit more about that later. The spectroscopy was also was now more passes in order to get more roll angles for spectral decontamination. Again, looking at multiple dithers and longer exposures, but this is also over that same 2,000 square degree area. And then in order to do the calibration that we talked about before, the design reference mission had in it a 20 square degree deep field, taking up about 10% of the total allocated time, that did imaging and spectroscopy to deeper depths to allow for understanding of systematics and flux limit effects, etc. Okay, so I'll just really quickly go down through how this works. For the imaging, again, to fully proper the PSF, we would like to do multiple dithers and then also tiling over a large area. So here is just one example of where this might look. So you do, for a couple of passes, you would do tiling over short and long axes, and then you come back at a different roll angle, and ultimately you're able to quite efficiently cover a large area that way. And these are just some simulated images from that paper showing what some of the galaxies you might expect to find in the survey. They look an awful lot like Hubble images, which is sort of expected. Although out in the near infrared. But the amazing thing, of course, is that you get 100 million of these. So again, it's really a step forward from what we could do in this waveband with Hubble. Okay, so in terms of the spectroscopy, looking at the total number of galaxies that we would be able to get in order to maximize the statistics for the for the large-scale structure measurements, the design reference mission aimed for a sensitivity of around 7 times 10 to the minus 17 ergs per centimeter squared per second for emission line for a point source, and looking at the way the overall structure or the overall survey structure came out, that gives you about 14 million redshifts using H alpha and another 3.6 million redshifts at higher redshift using O3. And so this is sufficient to do the large scale structure measurements that we were talking about, and this has been explored in papers and other technical work. Okay, so that's the basic design reference mission. That's where we're starting from. But as part of this community process, we got a huge amount of input from the community looking at other kinds of both science things that are, science cases of things that we can do with the mission, and also with the survey, and suggestions about how to configure the survey to optimize those science cases. And so in addition to the cosmology, these are the, well, we also had some white papers about cosmology actually, but if you look at, this is a word cloud about all the stuff that came in to the white papers and the science pitches. And while there's lensing and large scale structure here, a whole lot of the white papers were having to do with galaxy evolution, galaxy clusters, galaxy formation, black holes, AGN, circumgalactic medium, etc. And so this is the huge amount of additional science that we can optimize for, while also actually being able to reach the requirements that we need for cosmology. And that's a lot of what our discussions have been about. So I'm going to run through them super quickly, but just a few examples of the kind of white papers, science cases that we learned about, and this is going from close to farther away. There's been some really interesting science we could do for solar system objects, studies of ultra-cool dwarfs in the wide area survey, resolved stellar populations and low surface brightness structures in nearby galaxies, galaxy emission line diagnostics across a wide wavelength range with the GRISM spectroscopy, and then how that can be applied, for example, to AGN and black hole evolution. And then were a number of inputs about very high redshift universe, sort of looking at very early galaxies and the growth of structure through reionization, and then also how galaxies evolve, for example, in clusters, of which you can find a lot of in these wide area surveys. So that's just a little hint, sort of, quick flavor of the kind of broad science that was presented in the white papers and the science pitches that we looked at. And so there's been a lot of input. We summarized all these things. We had many different discussions about all the different input, but I think you could probably summarize ultimately the input from the white papers and the science pitches, the sort of conclusions that we drew from that, you can summarize with two main points. One of which is that many of the white papers and science pitches emphasize the value of relatively wide, deep fields for getting large galaxy populations and populations of faint galaxies. For example, looking at this, the populations of galaxies at high redshift. And so one of the things that we have been exploring extensively is deep fields larger than the 20 square degrees that were in the DRM. Not necessarily because it's required for the calibration, although of course that would help, but because there's all this other science you can do with these. The other one, the other main point that has motivated us is that there are a number of white papers and science pitches demonstrated the potential of an extremely wide, shallow survey in a single band, basically taking advantage of Roman's large field of view and survey speed. We saw that this is useful for many general astrophysics applications. And it also maximizes the number of galaxies you can get for cosmological weak lensing measurements. So in principle, helping the cosmology, but at the cost of some systematic uncertainty due to the fact that you don't have color information. So there's a trade-off there, but we are exploring a design that has an additional wide tier over a single band instead of all multicolor imaging as proposed in the DRM. So those are the two big differences in terms of the architecture that we're looking at for the survey relative to what was in the design reference mission. So that brings us to where we're at in terms of the nominal survey plan that we are considering at the moment. And one way to think about this is that we now have, rather than just a wide area and a deep area, we have 3 tiers, a medium, deep, and a wide. So the medium and deep tiers broadly correspond to the design reference mission in terms of bands and in terms of depth. With some adjustments in the area, so making the medium tier a bit smaller, potentially, making the deep tier a bit larger, and just pointing out again that the deep tier is essential for the calibration of the medium and wide tiers. And this is not to scale or anything. This is just to demonstrate the fact that we have these 3 different tiers. In addition to that, we are considering a wider tier that's wider than anything that was considered in the design reference mission, that would look for just a single band. As I pointed out, this is useful for cosmology and general astrophysics and is advocated by a substantial number of white papers and science pitches. And the area that we're looking at the moment for this would be something like 4,000 square degrees. But I'll talk about the considerations of this in just a minute. And so, given all this, this is now the framework that we're looking at, and we're considering various trade spaces in terms of depth, area, and bands, field location, observing strategy, et cetera, that will be optimized, in this framework. Okay, so what I'd like to do now is just sort of go through each one of those sets of trade spaces. So in order to do this, we've actually divided into individual working groups that have presented their own thinking on each one of these things. So for the medium and deep areas, again, this is the survey that broadly corresponds to the design reference mission in terms of depth and bands. The depth would be broadly set to maximize the number of galaxies for weak lensing shear measurements. And turns out that 140 second exposure, the depth that you reach there, is pretty close to the most efficient depth you can get, given observing overheads and other things, for actually maximizing this number of galaxies. So there are some small tweaks around that, but that was where, from the design reference mission, that was where that exposure time came from. One thing that we've been considering is to the extent to which we need to have full color information over this entire medium tier. And so it's possible that the medium tier could be either uniform, so for example, having 4 filters over the whole medium tier, as in the DRM, or you could potentially have a larger area with only 2 filters and a smaller area with more filters, which you could think of now as sort of a 4-tier approach that combines, that splits the medium tier into 2. And how we're looking at the details of, for example, how much color information you really need to accurately do the weak lensing measurements, and what is important for calibration. So for the deep tier, the trade-off there is fairly straightforward. You have to make sure you go deep enough over a wide enough area to be able to properly do the calibration for the weak lensing measurements, so that and for the large-scale structure redshift measurements, so that that's not a big limiting factor. But once you have reached that, then you have a trade-off of going deeper, which would be better for some of the higher redshift science cases, or wider, which would be better for for getting more galaxy numbers, and also to mitigate some aspects of cosmic variance. And so that's another consideration. And then one other consideration that came up a lot was recommended in a lot of the white papers, is exactly what filters we use and whether we add some additional filters. And in particular, the K filter, the longest wavelength filter, is something that a lot of white papers advocated for, because of all the great things you can do with long wavelengths observations, for example, in accurately measuring stellar masses of galaxies, being less affected by dust reddening, et cetera. And so we are looking at possibilities where some of the survey areas could also be covered by the K-band. The K-band is less sensitive than the others, and so it doesn't, at least in our look at this so far, it doesn't necessarily make sense to cover the whole area to a similar depth with the K-band, because that would be prohibitively time-consuming. Okay, so another consideration has to do with where we put these fields. They're pretty big, but at least at the moment, we're not thinking of covering the whole sky. So we're talking about somewhere up to 2,000 square degrees, and then smaller areas in the deep fields. There are a lot of considerations here. This is kind of a complicated trade space, and so I don't have any clear conclusions for you. I can go through one particular iteration of what this might look like later on if anyone's interested. I have that in my backup slides. But some of the considerations we've been looking at are complementarity with the wide tier and also the high latitude time domain survey, which itself is doing a deep tier in one particular area in the continuous viewing zone. The overlap of the field of regard with ground-based instruments. There will be a lot of people who want to follow up these fields from the ground, and obviously, telescopes are in different hemispheres. Overlap with existing wide area surveys. So we got a lot of white papers from Euclid, from Rubin, from Subaru about the amazing science that you can do and overlap in each of those areas. And so we're sort of considering all that. There's also some exciting solar system science considerations. And the closer you get to the ecliptic plane, the more likely you are to, depending on your cadence, et cetera, to be able to detect some really interesting, for example, trans-Neptunian objects. Then there is some consideration to timing in terms of which fields actually get done first. Another key question is actually how many deep fields we have. Do you have just one deep field where you have, it's sort of a contiguous area? Do you split it into multiple ones? How many fields would be useful? That's all a consideration that we've been thinking about. I'll talk about that more in a minute. And then finally, it's important to think about zodiacal foregrounds, where you are relative to the ecliptic, et cetera, determines a lot in terms of how what your foreground looks like in the near infrared. Okay, so that's those are all the considerations. I don't have an answer for you as to what this looks like yet, but just to let you know where we're at. And then the trade spaces that go into the wide tier, again, this was something that was advocated for in a number of white papers. So there's been a lot of careful thought into this. And I can sort of spell out where we're at and also the roads that we have currently not taken. So the overall strategy is there's some sort of basic principles that we laid out here. One is that we require sufficient sampling of the images in order to be able to do the weak lensing shape measurements. And so that's one. So a single pass with a single exposure doesn't necessarily work. You get a lot of chip gaps, or you get only a single roll angle. That makes it hard for doing the weak lensing measurements. In addition, we focused on the H band, the F158 band. That's the one that is the most efficient for doing these measurements in terms of the number of galaxies that we can reach to the required depth. And so the aim is primarily then just to balance depth versus area to maximize the number of detected galaxies, because that's good both for the cosmology measurements, the weak lensing, but also it's useful for all the other general astrophysics questions that we got. The working group that looked at this thought that this group that should generally go in the southern equatorial sky, because there's most overlap both with LSST and with upcoming sensitive CMB surveys. But the detailed field choices are still to be determined. And there's a lot of overlap with northern hemisphere telescopes that could still be achieved by going in the equatorial sky. So there's a lot of detail to be worked out there. The idea would be to use, at least to start with, just to do a single pass, but with multiple dithers, to give an exposure time similar to or shorter than the medium tier. So the design that we're thinking about at the moment has only one pass, so only one roll, but multiple dithers. And in terms of scheduling, it may be preferable to schedule this after some of the deeper tiers have gone, so that what we learn from them can actually inform what we do with the wide tier. And in particular, again, this gets into this question about how well can you do cosmology in these cosmological measurements, the shear measurements, when you only have a single band rather than additional color information. And that's something that we can begin to test out once we have the data from the other tiers that have multiple bands. So in terms of things that that we're currently not thinking about with these, there are a lot of surveys that suggested using the W band, the very wide area, or sorry, wide pass band for this survey, just because it maximizes the number of photons that you get in a given exposure time. And there's some really cool science that you can do with that, but the committee felt that it was very clear that we would be limited by systematics and the shape measurements the wider your bands get. And so we're not pursuing that at the moment. Also, not necessarily pursuing doing a very wide area in the K band because it's significantly less sensitive than the other bands, as we mentioned before. And not necessarily considering doing a very large area like full SST, full print, or the full sky, because you wouldn't be able to do multiple dithers. This would limit your ability to actually do the weak lensing measurements with Roman, which are prime driver for the mission. So that's sort of where we're at the moment. We're welcome to any feedback or thoughts that people have on this. One thing to note with this, and again, it's of interest, I think, given how many people wanted to use Roman for a really wide area survey, is that the overall scale of the wide tier is limited by the fact that we have a limited total exposure time, and by the fact that we have to be sure to meet these other cosmology requirements, including systematic errors. So it would be very, very challenging to be able to do all those things in the context of this particular core community survey. I think what we have learned, though, is that there's a lot of really exciting potential general astrophysics surveys or future surveys that could come along that would be also utilizing the capability of Roman to do this stuff. So I'll mention that a little bit later on. Okay, so with this, we have some outstanding technical questions that we are engaging with the project infrastructure teams to address. This is just a small subset of them, but just to give you a sense of where we're at. One is, what, as I mentioned before, what are the minimum area and depth of the deeps observations to actually allow calibration of the wider tiers? If we just do the single pass, as I mentioned before, for a wide area in a single band, is that actually enough to really do weak lensing shear estimation? If we only have 2 bands of imaging, is that enough for doing to support a GRISM spectroscopy program? In other words, can we use those 2 bands well enough to decontaminate the GRISM spectra as long as we have enough roll angles? What are the technical considerations for contiguous fields versus splitting tiers? So, we talked about a deep field going in multiple places, but the other tiers could also be, not necessarily contiguous. And there are things like edge effects, cosmic variance, also issues of scheduling that may make it easier to actually split things up like that. And so we need to look at those details. And then finally, one thing that's come up recently is what is potentially be very powerful to do cross-correlation measurements of the imaging and spectroscopy that we get with Roman with next generation measurements of the cosmic microwave background. And so those may inform, for example, the field choice to make sure that those overlap. This is not everything. This is just a subset of some outstanding technical questions to give you a sense of what we're thinking about. Okay, so I think that's my half hour. So that's where we're at the moment. I have a few other technical slides that I'm happy to share. People have questions, but this is the link to the questionnaire about that Rob mentioned before about filling in both a sense of how these town halls have gone, but also some further feedback. You can always also reach out to Risa and myself if you have any input. And just to emphasize one more time, the key thing is that many of the science cases and the white papers and the science pitches were not able to be concluded or included in this core community survey just due to the fact that we have a limited total exposure time and we have these other requirements that we need to meet. But a lot of this stuff would make really compelling general astrophysics surveys, and the community is always very welcome to propose for those. And so I hope that some of this stuff continues percolating through and actually maybe, informed by the performance and other aspects that we see once we actually carry out the first set of these core community surveys. So, this is a multiple year process, and hopefully we'll get many years of excellent science from Roman. Okay, I will stop there and take any questions. Thanks.
Let's thank our speaker by giving some clapping hands emojis. You can click on the little smiley face on the bottom of the window and click the hand icon there. Now we have time for questions. You can do that one of 2 ways. You can either write your question into the chat, and I'll read it out loud, or you can raise your hand and I'll call on you to unmute yourself. And then just like Ryan mentioned, please do fill out the feedback form. I just put the link to that in the chat, or you can scan that QR code on the slide right here. And also please join the Roman community by going to our outer space page as well. So I'm seeing one question in the chat. Arjun asks, thanks for the great description and hard work on this effort, Ryan and company. I'm curious why the full sky survey is not being considered currently. Is this just because the limitation of the 540 days? It seems to me that a single pass with multiple dithers to alleviate the PSF issue done early in the mission could really leverage proper motions and other galactic and extragalactic science by second and third epochs later in the mission lifetime. And then they have a second question. Also, to what extent does the overlap coverage with LSST for the medium area survey mitigate the need for 4+ bands of Roman in those areas, which might free up some time for an all sky survey? And then finally, could asking ROTAC for more time make this path, could make this happen?
Thanks, Arjun, and my other committee members who are here. Please feel free to jump in if you have any additional thoughts. I don't see if anyone else is there. Oh yeah, there's Risa still here. The main reason why this is why we've moved away from looking at all sky is exactly as you said. It's just the limitation of 540 days. I think we did. I mean, one of the challenges, as I'm sure you're aware, with doing short exposures in a single band over a very large area is that you're getting to the point where the overheads become a majority of the observing time, just to slew and settle for being able to do this. And so it gets sort of more expensive per bit of exposure time the wider area that you go. Looking at in terms of the overall portfolio of the things that we need to reach, it became clear that something of the whole sky is just not going to fit into this into the observing time that we've been given. Just to say, I agree wholeheartedly with your point, which is that doing one early in the mission could get proper motions and other galactic and extragalactic science that then could be utilized later on. So there is really an argument for doing, if we do a large area, to do it as early as possible. And this is really an interesting trade-off, because at the same time, I think it's become clear when talking to folks with a lot of experience in this, including people on the committee, that at some level we don't really know what we're going to get. It's true with any mission until we actually get the images down. And so the optimal, so we could schedule everything really early for our widest tier, which would then give the longest baseline for things like proper motions, absolutely. But that may then give us what's not an optimal observing strategy if we're able to make some adjustments afterwards. So yeah, I mean, so that's where we're at for the first question. For the second question, what does the extent of overlap coverage with LSST for the medium band mitigate the need for 4+ band? We are exploring that technical question right now. And I think the idea is that indeed that if we really don't need the 4+ Roman bands over the large area, and we actually would have enough, we would have good enough coverage just with, say, 2 bands, that would indeed open up time to widen a wide tier. So that's something we're exploring at right now. And in terms of asking the ROTAC for more time, I mean, we can always advocate. At least in the way that this has gone so far, the sort of guidance for the mission has been fairly clear as to what the allocations are for each one of the surveys. To be honest with you, like if it wasn't for the goal of doing, as you pointed out, of doing this stuff really early, in order to get the proper motion baseline, I think that something like this would really make a fabulous use of, another large scale survey that could be considered over multiple cycles for general astrophysics. Anyway, so that is probably not exactly the answer you're looking for, but I hope that helps. One other quick thing just to say, in terms of the overlap coverage and whether we need 4 Roman bands or not, there's another important consideration, and I think I mentioned this in the technical questions, which is it's not obvious how many bands we need in order to also do the GRISM spectroscopy. which is also a key portion of the what we need for the cosmological requirements. And it may be that two space-based images in 2 bands plus ground-based images are enough to decontaminate the GRISM spectra, especially if we have enough rolls, but we don't know that for sure. So that's something that we're actually asking the PITS to show for us at the moment. Great.
Awesome. And then just, oh, go ahead, sorry.
No, I think that was great. I could try to address Jesse's question in the chat about the medium, whether the medium deep surveys alone could meet the weak lensing requirements. I think the answer to that is no. The wide field is really needed for the weak lensing requirements. I think, you know, the committee has been very actively discussing how we can cover as much area as possible because of the breadth of the science that is addressed there. But I think that the sense of the committee is that the way to do that under our constraints that we were given is to consider making the wide tier as wide as possible, but keeping the constraint of making it as useful as possible for weak lensing and making it a competitive weak lensing survey. So there has been discussion, and there actually is continued ongoing discussion, including in collaboration with the lensing and spectroscopy focused teams to ask about, you know, kind of what's the widest survey we could do that still meets those needs. And I think that comes some way towards what you're looking for. Get all of the way there. I just want to echo what Ryan said, that, you know, this survey is not the only way to achieve that goal. And I think there, you know, myself and many other people on the committee are quite interested in having Roman cover as much area as possible. But I think the way to get there is going to be some combination of this survey and community surveys.
And then Julie, go ahead.
I wanted to comment a little on pressure on observing time at the beginning of the mission. The Galactic Bulge Time Domain Survey has pressures related to their science requirements that drive wanting to schedule their seasons early in the mission. So I think you can reasonably assume that we're going to end up with 2 Galactic Bulge Time Domain seasons in the first year of the mission. So that's 4 months. We also have a requirement to schedule the chronograph instrument observations early in the mission. So that's another 3 months out of the first year before we've done anything else. By the time you add in that there are role constraints on aspects of the high latitude wide area survey, the ability to be very flexible in the first year and sort of schedule a large chunk of time to a wide area survey starts to become extremely difficult. I just, you know, I appreciate from a distance it looks like, oh, you've got the first year, you can do what you like, but we actually have a lot of pressures that drive from core mission requirements on that time. They're already in place.
Thanks, Julie.
Thanks, Julie.
Any other questions from folks? And a question from Harry in the chat: how are the figures of merit being used in evaluating trades?
Great question. Thanks, Harry. So there's some specific figures of merit for the cosmological measurements that were utilized in order to sort of set out what the requirements of the mission had to be in order to, you know, measure things like the amplitude of fluctuations, etc. And so those, at least for the design reference mission, there was a fair amount uh, uh, of leeway in terms of being able to meet those requirements, but those are still, we sort of looked at how much do we need to potentially, reevaluate those, and I think in the end, we decided that we could stick with the figures of merit that were there, and so we are certainly setting things up so that we must be able to, with significant margin, with at least sufficient margin, be able to meet the cosmological figures of merit. So the ultimately how many, it really ultimately comes down to, for example, with the weak lensing, of how many shape measurements you can do, and a little bit about what redshifts you're probing, etc. For other figures of merit, there is it's pretty challenging, and so we did get a helpful white paper, and thank you, Harry, laying out a figure of merit for example, being able to study galaxy evolution, and what would be the optimal way in thinking about what surveys you would do in order to maximize your understanding of galaxy evolution. I think it's, as probably anyone who's tried thinking about that in a systematic way knows, that you can go along a particular axis and find something that's really pretty useful. But if we look at the overall range of science that came to us, being super quantitative about it is fairly difficult. So we're certainly exploring the figures of merit that were presented to us. I don't think we have had really a good sense of any additional figures of merit that have come up just because of the breadth of the science that we've gotten, other than maximizing the number of galaxies with good coverage that you get within a particular area, et cetera. So it does make it a little tricky, actually. It makes, in particular, things like the field choice becomes challenging, because how exactly you decide what would be the optimum, say, multi-wavelength coverage that you can get in one of the deep fields, it's, there are so many variables there that it's very, very challenging to write down. So just to say, I think we have been utilizing figures of merit when they are available, but we have not, especially with the galaxy evolution science, given the complexity of it, we haven't focused our efforts on developing new ones, but more on, in a sense, looking at very simple things like, what is the redshift distribution if we do a particular observation? What is the total volume that we're probing? What is the total number of galaxies we get, et cetera. Okay, so Arjun asks, is there a possibility of splitting the widest part into two fields, one in each galactic cap? Yes, absolutely. Yeah. That is one of the main considerations, is where it would go. So the interesting question there is, again, to what extent do you want the widest area? Do you care about overlap with is it more helpful to get overlap with a single data set? Or is it more helpful to get overlap with, say, a uniform CMB map or something like that? Or is it more helpful to actually get overlap with as many possible different data sets as you can? I think there is, at least from my point of view, and I think there's some different opinions on this in the committee, from my point of view, making sure that at least a substantial part of the observing area is visible from as many ground-based facilities as possible. Not necessarily making an even distribution, but making them making enough to make it interesting across the board, is sort of in keeping with the community survey aspect of this. We would like as many people as possible to make use of Roman data and exploit it, as it were. So anyway, so there are a number of different considerations there, but I think we definitely have thought about splitting this wide area in two. And indeed, as I think I mentioned, for scheduling reasons, it almost certainly does make sense to have more than one contiguous region.
Any other questions at all? just got one for
Ah,
free.
GRISM surveys, right. So the at the moment, the plan that we're looking at has the GRISM surveys planned for only the areas that have multicolor imaging, which would be the deep and the medium tiers. And this is something, as I mentioned, I think before, that we're considering. The challenge of doing spectral decontamination with a single band of Raman imaging may be pretty significant. And so we're looking at really how many bands we feel like we need. But in order to do the spectroscopic cosmology measurements with the BAOs and the retrospace distortions, we definitely need to have spectroscopy over at least 1,000 square degrees, maybe up to 2,000 square degrees in the medium area. Whether or not that then extends farther to a wide tier where we only have a single band of imaging is something that we're going to have better input on soon. That's not currently the plan, but we also need to make sure that that the spectroscopic data that we are planning is sufficient to meet the level 1 cosmology requirements. If we go down to say 1,000 square degrees for that, then that may be challenging. So I'm glad you raised that. That's an interesting point of discussion at the moment.
And just a heads up, we'll be posting recordings of these talks on the Roman Community Forum website. I just put a link to that in the chat, so stay tuned. It should be linked on our website very shortly. And now we'll take any other questions that folks might have. All right, not seeing any hands, not seeing any other questions in the chat. So let's make sure we thank our two speakers, Ryan, our speaker today, and also Risa. Thanks again for muting yourself and answering questions as well. Really appreciate it. Thanks everyone for calling in today. Have a great one, and talk to you all soon. Thanks. Bye, everyone.
Thanks, everybody. Bye.